my name is Gbadegesin, and I'll be talking about the networking stack in Vista, some of the changes that we made, why it is that we decided to overhaul the stack at this point. And you can think of this talk as a continuation of the talk that John Lambert just gave on the overall security principles that went into the development of Windows Vista and how those were realized in a specific area, in a domain-specific area, which is networking. So just getting started, a little bit about myself. I'm responsible for the architecture of the Windows transports, which includes everything from TCPIP to legacy protocols. And it also includes everything from the network driver interfaces that our partners use to build drivers for Windows, up to the Windows socket stack and the HTTP stack. I've been working on various areas in Windows networking for about 11 years now. And the past 6 of those years have been spent on what I'm going to talk about today, which is the redesign of the stack. So I'll be sort of moving back and forth between a very detail-oriented discussion as well as a high-level discussion about how we were thinking about some of the things we were doing. Hopefully that'll give you a feel for not only what we've done, but also where we're planning to go in the future. The way to think about the stack is that it's really a starting point for a set of things that we want to do and ways that we want to advance the platform and secure the platform for the next 10 years. So how do we approach something like this? Well, I mean, you have an old stack that's up and running, it's working. People are more or less familiar with it, even if they may not be happy with it all the time. The only reason to replace a subsystem like that is if you can make a significant step forward in its functionality, in its security, in its extensibility. And the way to make that kind of leap is to look at it from a different perspective. The way that we approach it is that we try to imagine who are the customers for the networking stack. So we have end users who basically really only care that the networking stack works and that it gets great performance for them. We also have folks like administrators who care primarily that it doesn't cost them extra money to maintain the networking stack. In other words, deploying a network shouldn't basically result in a ballooning of their support costs. And the flip side of that is that they want it to be secure. Then we have partners who, everyone from folks who build systems like HP and Co. to folks who build hardware devices that plug into the operating system. They care that their devices are supported and that the systems they build have great scalability and deliver benefit to customers. And then finally, in many ways, the toughest crowd of all, developers. This includes everyone from folks who write software that runs on top of Windows to folks who build security solutions. A lot of the people in this audience may fall into this category. The reason they're the toughest crowd of all is that they have fairly clear ideas about how something like networking should work, and they're not afraid to tell you. So you have to take their expectations around having APIs that are rich and clean and being able to see into the networking stack and being able to extend it and balance it against all the other considerations that you have from all the other categories of customers that are served. You put all of those together and you come up with a set of fairly concrete, easily understood things that are going to guide what you do in overhauling the stack. So this is how they sort of break down for us. The first is that we wanted to achieve something that could be referred to as the state of the art. In other words, when you think about how a particular networking problem is addressed, whether it's how you run over high bandwidth networks or how you secure an operating system, a machine that has network capabilities, we wanted people to be able to point to the work that we've done and say, that really did advance the state of the art, and there's some really useful new thinking there. The second is that, and almost something that follows necessarily from that, is that to be the state of the art, you have to be extensible because the state of the art is always advancing, right? You have to enable people building new innovations, new ideas on top of the networking platform that you provide. And then the last two are also closely related in that in the same way that the state of the art is advancing, the security threats are constantly advancing. And to cope with that, the security profile of the system has to be constantly advancing. And you have to think through what that means for each of the capabilities that you build into the networking stack. So a little bit of history. Because TCPIP is such a low-level component, because it's kind of the first line of defense, we've been dealing with security issues much longer than virtually anybody else in the application stack in an operating system. So going back to early attacks, LAND-D, et cetera, which sort of focused on specific protocol vulnerabilities or implementation quirks, all the way to what we're seeing today, where you have denial of service attacks that are really more and more aimed at profitability. We've been there through the whole scope of that experience. We've witnessed the implementation of the security development lifecycle. We've had to put in procedures and processes to deal with these things long before, there was even before the ecosystem that we think about and kind of take for granted today existed. So as we replace the stack, we want to preserve that history. We want to preserve all of the work that we've done in the past, and we also want to advance and move forward. So I mentioned that we've been working on this for about 6 years now. So what does the timeline for that look like? Well, way back in '99, we started making the first architectural decisions and getting the system up and running bootstrapped. So our first milestone was basic UDP sockets over IPv6. An interesting thing that isn't commonly known is that the new stack actually began its life as an IPv6 only stack, and it was later that we added support for IPv4. The reason we did that is because there were certain capabilities in IPv6 that we wanted to make sure we had a consistent experience for. We didn't want to start with IPv4 and then bolt on IPv6 later. We started with the new networking protocols, and then we backported a lot of the logic from the IPv6 protocols into IPv4. The second big milestone was actually getting TCP data exchanges up and running between two machines running the new networking stack. That happened in mid-2002. And it also included some of the work that we did early on connection offload. And then the big milestone really is late 2003 when we were able to check in the new networking stack into the Windows, what was then Longhorn Windomain builds. So by this time we had already completed, basic functionality paths. We had already gone through a couple of internal security reviews. We had already built up a body of scripts that would allow us to exercise the capabilities of exercise a lot of the old attacks that were known for the old stack against the new stack. And that was how we were able to get in. So in many ways, the stack that I'm talking to you about today, that I'm about to start going into detail on, is already about 3 years old. And so for us, we've grown familiar with it already. Now, you can overlay this timeline on all of the product development that was going on simultaneously. The same team that was working on the new networking stack was also supporting Windows 2000. We shipped Windows ME and Windows XP while we were working on this. Windows Server 2003, XPSP2 was in fact a lot of the things that we did with the firewall and with the new changes in networking. They were backporting stuff that we had already done for the new stack onto XPSP2. And that just continued going down the line. We ended up backporting also some of our connection offload capabilities onto Windows Server 2003 SP1, which we talked about quite a bit at the Windows Hardware Engineering Conference a few months ago. So these are the folks who have been doing this work. The team has grown quite a bit since 1999. These guys include the folks working not just on TCPIP, but also IPsec, the base firewall platform, which I'll talk about in quite a bit, and then the tools and utilities that pull the whole thing together. This is a look at some of the architectural decisions that we made early on and that guided our work. But rather than sort of talking to this diagram, what I thought I would do is I would jump into the debugger, and for those of you who are familiar with the older networking stack, this will be an interesting look at how much exactly has changed and how we've rethought a lot of the things that we've built. So let me switch over to command prompt. What I'm going to do is I'm going to use the user mode debugger. So I'm actually looking at the system that's projecting this presentation on the screen right now. So the first question is, how do modules actually fit together in the new networking stack? What we did is we wanted to be extensible. So we started out with IPv6. We wanted to easily be able to drop in IPv4 support without having to change anything in TCP or UDP. Right? So what we did is we defined what the broad levels of functionality were, and we defined interfaces for components to talk to each other. And I can enumerate some of those components right now. So for instance, I can dump out, actually, so this is a list of just some of the components that are registered as clients of the various interfaces that we expose in kernel mode. I won't go into detail about this except to show that at any given time we know exactly what's running and how the components interact. Similarly, I could dump out a list of the providers. This architecture of bringing components together flexibly allows us to do things like our test team has harnesses that they can execute that will wrap the TCP implementation at the top and at the bottom, and that will actually exercise the entire TCP state machine and all of the various APIs that we provide in isolation from IPv4 or IPv6. So if there's any capability that's in the interface, we want to be able to exercise it, even if it's not something that you would see in a normal deployment on the network. So that was a key thing that we wanted to get out of this approach to bringing components together. Similarly, when you actually look at the implementation of the network protocols, we wanted to share as much functionality as possible. So if you think about how the functionality breaks down between TCP and IP, TCP maintains things like connections and endpoints and so forth. IP maintains addresses, interfaces, and so on. We sort of we manage that split as well fairly consistently. So I could dump out, for instance, a list of all of the components that are registered as transport modules. And on this system, I have a UDP transport, I have a TCP transport, and a raw transport. I can dump out the contents of these structures. So let's take a look at the UDP. And you can see sort of how it connects with both TCP, with both IPv4 and IPv6 at its lower edge, as well as with clients on top. Similarly, I could dump out the IP, let's say IPv6 state, which includes everything from its configuration to how it manages communication with upper layers and how it manages addresses and so forth. So if I dump out, for instance, the interfaces, actually that's something that's more easily done from. So here's just a quick look at NetShell, which is a command line program that we built to make it much easier for, without using the debugger, to look into the state of the system. So I can dump out the list of the network connections that I have, both the ones that are connected and the ones that aren't. I can switch back to the debugger and dump out a list of all of the addresses that are in the system, including both IPv4 and IPv6 addresses. So that covers a little bit of how components fit together and how we maintain runtime state. Similarly, I could go into quite a bit of detail about how we handle I/O. That has also changed significantly since Windows XP SV2. However, the reason that I'm sort of giving you a feel for how much scale of change there is to pose the following question. If you have a solution that's been built for the old networking stack, what does all of this change mean to you? In other words, how do you move from the old world to the new world? This is something that we had to give quite a lot of thought to, because out of the gate, we wanted as much capability as there was on Windows XP SV2 in terms of securing the system to exist on Windows Vista and more. The basic problem I'm asking here is the following. When you think about what you're doing with security solutions, what you're doing is you're looking at the runtime state of a system, the operations that are going on, and you're enforcing policy decisions around those. So for instance, this particular application cannot connect to the following website, or the following words are considered bad and they should be edited out of websites, for a parental control application. And in the Windows XP stack, it was fairly difficult to do that. You had to plug in kind of blind at these gross interfaces. Either you could look at the packets that are getting emitted by the networking stack, or you could plug into the TDI interface or have a WinSock layered service provider and try and kind of divine or intuit what's happening inside the stack from outside the stack. So that's this picture. So this is what you used to have to do, and you'd basically be trying to figure out this state machine, which is a fairly rich state machine and complicated, from the packets that get emitted or the API implications that you see. That tends to limit what you can do in terms of securing the system. The key observations that went into redesigning the networking stack were that if you want to enable people to build security and extend the security capabilities of the networking stack, you have to give them visibility into what the stack is doing. You have to give them ways to directly control the behavior of the stack. So, for instance, reach into a state machine and say, no, this transition is not allowed because of the following reason. And then finally, you have to decouple all of this. You have to decouple the ability to control the stack's behavior from the stack itself, so that long after we ship, the behavior of the stack can continuously evolve in response to threats. That's the way that you build a networking stack that can keep pace with security threats without being bound to binary releases of code from the operating system vendor. The result of that is the approach that we took in the NetIO stack. The basic way to think about the approach that we took is that we took anything that we could think of that seemed like it was a policy decision that we might be making inside the stack. We tried to externalize that and provide interfaces that would allow an external component to tell us what to do in that situation. I can show you what that actually looks like in the debugger. If I dump out a set of routines that start with, for instance, the prefix inet inspect, what these are essentially routines that are implemented in the stack that are callouts that we invoke to ask someone to tell us what to do. So for instance, if someone tries to, say, acquire a port, so a port assignment, that's something that we will actually turn around and ask an external security component, can the following process acquire the following port that it's trying to take? If there's no security component installed, then we'll just do whatever the default behavior is. But across the board, at every layer in the stack, we're continuously asking for permission to do everything that an application is trying to get the networking stack to do. So you can think of that as decoupling the state machine from the policy that's behind the state machine. And then what we did is we wrapped it up, we took that capability and we wrapped it up in what we call the Windows filtering platform. The Windows filtering platform is the way to think. I'll give you a pictorial way to think about it and then kind of a more concrete way to think about it. If this is the networking stack, so kind of you think of a flat plane, RPC on the top of Windows sockets, and then you have TCP and UDP and IPv4 and v6 on top of that. This is kind of how the Windows filtering platform changes that picture. This will be a little hard to see because the colors are light, but you can see that from the stack there are callouts that are flowing through things like secure sockets, application layer enforcement, and these built-in components that know about networking policy. And then as a second level, you have a base filtering engine and a core filtering engine that exists to help third-party components plug into this infrastructure and also influence what's happening inside the stack. The final step is the things like IPsec policy, firewall, and so forth. They are the ones that actually implement customized policy around what the networking stack does. So a more concrete look at what was in the picture. So you have the core stack and built-in policy-related components like application layer enforcement that keeps track of processes, threads, and so forth, and what the operations are at the application layer. We've built a stream inspection module that allows a third-party component to subscribe to a particular TCP stream. So for instance, if you want to edit the contents of the stream or just inspect, you can actually take out bytes from the TCP data stream and put in replacement bytes, and the stack will take care of fixing up any sequence numbers and so forth to make it look transparent to the application. And then finally, IPsec has its own filtering logic around when an IPsec is negotiated between various machines and how policy arbitration happens. So those are the elements the built-in elements. And then we have the core filtering engine and filtering callouts. The filtering callouts you can think of as components like antivirus, firewall components, parental controls that basically provide filters saying I'm interested in these kinds of operations, and then the stack makes sure that they get to see those operations and that they can say, for instance, block those operations or suspend them while they go off to user mode to get permission and so on and so forth. So the way that we've broken up everything that happens inside the networking stack is we've defined the notion of layers. So we have layers all the way from RPC that let an application plug into the RPC engine itself and understand what it's doing at that level and control operations at the RPC level. You can also plug into operations at the socket level, things like listens, accepting connections, establishing connections, and assigning ports. You can plug into the data stream. You can plug into the inbound and outbound messages that get emitted as the result of all of these state machines or as the result of applications doing I/O. And then finally, control traffic can also be inspected through the filtering platform. So I'm going to take this question. We have a lot of slides to get through, so if it's not a deep question where something just doesn't make sense, try and defer it to the end. I'll also be in the booth afterwards, but your question? I'll talk a little bit about that towards the end. So what does this enable? The biggest thing is extensibility. The other thing is transparency, because by exposing the operations inside the stack, it gives you a much better feel for what's happening. I mean, you shouldn't be wondering how Microsoft implemented this algorithm inside the TCPIP stack. We'll just tell you what the state machine is, and then you can participate in that state machine too. And then finally, the fact that we built this tightly into the stack means that we can do all of this and still maintain really good performance, as opposed to what you would get if you had a third-party kind of plugging in on the peripheries of the subsystem. So that's to give you an idea of how we approach the question of how do we make sure that the security profile of the system can continuously evolve. We have a beta program around the Windows filtering platform, and we have most of the leading vendors are already aware of this. This is also a platform that can be used for developing your tools and doing research. If you want to understand better how networking works, or if you have particular ideas for how to change the behavior of a networking stack, what we've essentially done is we've tried to build the basic scaffolding that anyone would need by just using Windows Vista in this mode, and we're basically giving you a stack that you can customize and you can make it behave more, for the most part, how you want without having to write all the code. So that's the platform piece of what we've done and what we've done to try and make it easy to extend. I'll switch now and I'll talk about what we've done for applications. So one of the biggest problems that network applications have is figuring out when am I connected to the network so I can go off and use some website. And we've put in some capabilities in Windows Vista to actually make that quite a bit easier. So the problem is, how do you detect for a particular internet connection that it's actually the internet? There's a component called Network Location Awareness, which has a couple of algorithms built in to try and answer that problem. So the first basic idea is that imagine you have a PC that's plugged in. It has multiple connections, a wired connection and a wireless connection, and you want to figure out which connection is good for use on the internet. In this case, I've shown a wireless hotspot, which won't get me to the internet because it's just spoofing DNS queries. The basic approach to detect this fact is to send a query for a known DNS name, and for instance, for a text record, and look at the response. If the response is what you expect, then you can conclude that it's the internet. And you can take this further, and actually customize this so that you can detect different kinds of networks. So for instance, a corporate network, and so on and so forth, just as a heuristic to give you a good feel for whether you should launch certain operations or not. Similarly, you might have a scenario where you do have internet connectivity, but you're going through a transparent proxy. And for certain kinds of applications, it's important to know whether there's someone in the path between you and your final destination, whether you're being proxied. And the way to solve that, the way that the Network Location Awareness Service solves that problem is we send a request for a known URL, And if we get the response we expect, then we know it's the internet. The other thing that we also do is that we also look at the time to lives that we get back on multiple requests, and if they're all the same, going to multiple destinations, we know that by definition someone must be terminating this connection and then proxying us out without our knowledge. So this basically restates what I just mentioned. The fact that this is a built-in capability means that it's much more scalable, and multiple applications on the same system can take advantage of the basic capabilities. The other key thing about this is that it works for both IPv4 and IPv6, which is a key point because IPv6 is enabled by default in Windows Vista. I'm sure many of you have heard, and your level of connectivity may differ between IPv4 and IPv6. So for instance, for IPv4, you might have only site local connectivity. You might not be able to receive connections from the global internet, whereas your IPv6 connection may be able to receive connections from the global internet, and vice versa. So it's important to be aware and cognizant of what level of connectivity do I have, what kind of environments am I in, and to have that logic built into the core networking stack itself, which is what we've tried to do with the network location awareness capabilities. So second big challenge. Another thing that happens with IPv6 is that you have a lot more addresses than you had with IPv4, right? IPv6 has link local addresses. It has site local addresses that have been deprecated, but you still have global addresses, and you may have dozens of, link local and global addresses on any given machine. So the question arises, if I want to connect from, point A to point B, which of these addresses do I use? If you think about what that works out to, you have this PC, again, is associated with the hotspot as well as having a plugged-in connection. The hotspot address has its own address, the hotspot interface has its own addresses, and then the wired connection has its own addresses, and then the server that it's connecting to has a bunch of addresses as well. So if you try to take the cross product of these, you'll spend a lot of time trying to figure out which one of these is the right connection. The way that we've approached that in the platform to make life easier for applications is that we just provided new APIs, connect by name and connect by list. And these APIs are designed so that you can simply say, I want to connect to the following list of addresses, or I want to connect to the following name. We'll go off and resolve the name. And then underneath the covers, we'll try and optimize the connection establishment process, looking at information from a variety of sources. Currently, what we do is that we just simply try one combination at a time. This is another area where we'll be doing additional work in the future to make that a lot smarter, and to also allow you to put in security parameters. So for instance, saying I want to connect with the following security, using the following security settings. All right, so port management. This has been an area that has been a source of feedback in past platforms. So the key thing is that in Windows Server 2003 and earlier platforms, the port range from which we assigned ports dynamically was 1025 to 5000, which conflicts with the actual registered ports that are assigned to a lot of applications. So if you actually look at a Windows Vista machine and you do a netstat, I'm not sure if I have any connections because I don't actually have a network connection, but I can also show you this from NetSH. If I go to IPv4 show dynamic port range for TCP, what you'll notice is that we're now assigning ports from the IANA specified range, meaning we start at 49K and we go up from there all the way to 64K. So if you had any registered ports in the lower area, first of all, we won't be conflicting with those. The other thing is that not only will we not be conflicting with those, but we also have more ports available for dynamic port assignment. On top of that, we also implemented support for randomizing port number assignments. So if you have an application and you'd like to sort of do a secure connect where it's harder to predict what port number your application is going to use when it's making a connection out, we introduced a socket option as a randomized port that will allow you on a per connection basis to basically say that you want a random port number assignment for your outgoing connection. So that's one set of capabilities around port management. The other set of capabilities has to do with applications that essentially need to do either their own port management or that need support for securing their network ports. So taking the first case category of applications, so you might have a conferencing application that, for instance, needs 100 ports and it's going to manage those ports itself. So we have support for doing that as well in the networking stack. The application can submit a runtime request for a block of ports, and if we have enough ports available and the application has the right privileges, we'll actually give back a block of those ports, and the app can manage those on its own in parallel with the stack managing port numbers for everybody else. That addresses one style of application. Another style of application has to do with services that might be concerned about squatting. So you install, for instance, IIS on port 80, or you install RIP, the Routing Information Protocol on port 520, and you want to make sure that when you connect to port 520, it's actually, IIS or RIP that's there. Currently, if the process is not running, in the past, there wasn't really a good way to lock down that port. So what we've done now is that we've actually built in APIs in the IP helper API so that you can reserve ports statically ahead of time. So for instance, when you're installing an application, you can actually say, I need port 520 in order to run. Please lock down port 520 and don't give it to anybody else, even if I'm not actually running at that time. And once the application has done that, we give back a reservation token that the application can use in conjunction with its privileges to obtain that port at runtime if it needs to, and use it to bind its ports and accept connections. So a quick look back at what I just said about how port management has changed. There's the IANA compliance for registered and ephemeral ports. That's something that security solutions in particular should probably be aware about. You're going to see different behavior in the port management space. Also, as applications start to take advantage of the new support for randomizing ports, that's going to change the behavior you see coming out of applications. And then finally, the port reservation is something that's really useful for application vendors. So now I'll switch gears completely and talk a little bit about how we approached the challenges around TCP performance and then handling intensive workloads. So a lot of our work and a lot of our thinking went into this area. So core TCP performance, to understand some of the things that we've done there, it's useful to know a little bit about flow control. So I'll breeze through this since I'm guessing a lot of people here probably know about this. There are two algorithms that kind of determine TCP performance. The first is flow control, which really runs on the receiver and is used to manage the flow of packets from the sender to the receiver. The second is congestion control, which runs on the sender and which is used to make sure that the network doesn't get overloaded by a particular TCP connection. So flow control first. How it works, the receiver advertises a window. The window is the number of bytes that the receiver is willing to accept. The sender can send that many bytes, and then it has to stop and wait for an acknowledgement from the receiver before it can send more. So that's a basic idea. Now, what window should the receiver advertise? The ideal window is the product of the bandwidth and the delay. What does that mean? Well, you can model the path between a sender and a receiver as a pipe. The receive window capacity is essentially a particular volume cross-section of that pipe. So in this case, I've shown how much of this particular pipe would be used by the particular receive window that's being advertised by this receiver. So the length of the pipe is the delay, and the cross-section of the pipe you can think of as the bandwidth, how many bytes you can send at a given instant. So now if you take this receive window and you overlay it on top of a pipe that looks very different, you get a very, very different throughput. So now if your receive window is fixed, this is the kind of behavior that you see. You go from a network where the receive window is fine to a different network and your throughput tanks. So this is a numerical way of looking at what I just showed pictorially. So you can see what the ideal window would be for various paths with various speeds and round-trip delays. And then you can also see what the capacity is that would be utilized by a default window, for instance, on an operating system that doesn't have any dynamic behavior around its window size. and that just uses, say, the 64K default, which is the maximum that you can use by default in TCP. The way that we approach this problem is that, first of all, we know that we need to be able to adjust the receive window dynamically. So every single connection that's negotiated by the Windows Vista TCP stack will try and negotiate window scaling up front. And that'll give us some sort of leeway in terms of how we can grow and shrink our windows later on in the connection. The second thing that we do is that we estimate the capacity of the pipe between the receiver and the sender. And that's a fairly tricky problem to solve, because when you're the receiver and you're not necessarily emitting packets, your only source of information on what the pipe's capacity is what arrives from the sender. And so we put in quite a bit of research on getting a good algorithm for estimating capacity in this environment. The final thing that we do is that we vary our window advertisement based on that estimate that we generate. Now, if you think back to the pictures that I showed you of the two different pipes, you can see that clearly there's quite a bit of room for improvements, in moving from one network to another if you have this kind of capability. And that's in fact what we've seen. So our Microsoft.com folks actually, in testing the particular path that they had between Tukwila and the Bay Area, a pipe that they had never been able to saturate in the past, right out of the gate got a 40x improvement, just for plain TCP throughput. Now, not all applications see that level of dramatic improvement, and the big part of the reason is that applications typically, a lot of applications have their own flow control that they're doing on top of TCP. So for instance, the request response application sends a request, waits for a response, sends another request, waits for another response. If you can imagine the request traversing that humongous pipe and the response sort of making its way back over that humongous pipe, it's like the problem of leaving the pipe idle. So the way to solve that problem is to build pipelining into the application so that it can send multiple requests to sort of prime the pump, and then the responses can come back and keep the pipe full at all times. An example of an application that has that behavior is SMB 1.0. So by default, SMB 1.0 doesn't have any pipelining capabilities enabled. So when you move from, say, a corporate network with low delay to a high-speed network, you don't get very good performance. With SMB 2.0, which is enabled by default in Windows Vista, it actually does have support for pipelining, and we've done a bunch of work on tuning SMB 2.0 performance so that when you compare SMB 1.0 on the Windows XP stack to SMB 2.0 on the Windows Vista stack, we get an even more dramatic improvement than what we got just with raw true TCP performance. So there we go up to 46x improvement. The first thing that happens, when we enable something like this is people want to know how to control it. So what we did is we actually have that capability built in. So if I show, let's see. We have a bunch of global settings that can control TCP's behavior. One of them is the auto-tuning level. So by default, this is set to normal, but on particular networks, admins might be worried that a signal laptop can actually saturate a gigabit link without much effort. So if they want to control that, we actually give them a way to do that. Either you can do it in the command line, or you can also do it using group policy and just roll that out to an entire enterprise. So that's a quick look at one feature that we did for TCP performance that's really targeted at end users. Now I'm going to switch gears and look at some of the stuff that we've done around handling intensive workloads that matters more to high performance applications, whether it's web servers, proxies, etc. The ways to think about tackling these workloads is there are multiple dimensions of scalability. One is bandwidth scalability, another is memory scalability, and so on and so forth. So looking at bandwidth scalability, what are the challenges? Well, at a gigabit, you have a budget for how much time you can spend processing every single packet that comes off the wire. At a gigabit, you have about 16 microseconds, and if you spend more than 16 microseconds per packet, you're going to fall behind and you start dropping packets. At 10 gigabits, that goes down to 1.6, and at 100 gigabits per second, you're down to about 160 nanoseconds that you can spend processing every single TCP segment that comes off the wire. So now if you want to build a stack that can scale to these levels, clearly you have to kind of rethink some of the ways that we approach the problem. So we've done a number of things. So we process multiple packets at once. We offload checksum computation and verification because that's not really something we have to do with the host CPU. And then we offload actually chopping up segments onto the wire. But it's still not enough to get to 100 gigabit throughput. So how do we get there? Well, we actually have to take TCP processing and move it off the host operating system so that the only thing that we deal with in the operating system is handling requests. So for instance, a send, a receive, we can deal with the rate at which requests arrive. It's just dealing with the rate at which packets come off the network that becomes challenging. So how do we get to the level where we're dealing with requests rather than with dealing with packets? Well, we build in the intelligence into every single layer of the stack such that it looks at the state that it maintains, and it has the ability to package up that state and pass it to a piece of hardware. So that happens at the TCP layer, at the IP layer, and at the sort of ARP layer, if you will. So now what happens is that, looking at what happens when we look at a connection and we figure out, okay, we're starting to fall behind on this connection, and we have an offload-capable adapter, we need to move this off the operating system and into hardware. So what happens? So we initiate an offload attempt. TCP packages up the state for the connection and passes it down to IP, which packages up the state for IP and passes it down to ARP, which packages up the state for ARP and passes it down to the network adapter. And then the network adapter can either accept the offload or it can reject it. If it accepts the offload, what happens is that we then percolate back up the stack, kind of doing a two-phase commit. If there have been any changes to the state on the way down, this is our chance to fix up those changes and notify the NIC that, say, for instance, the algorithm has changed, or we have, a different sequence number now because we accepted some data while we were in the process of offloading. So from that point forward, our state machines are synchronized between the operating system and between hardware, and we also have a channel where we can communicate changes to that state. So the key thing is that this is graceful. It's transparent to the application. So the application does not know necessarily that its connection has been offloaded, although it can find out. If you look back at the state at the options that I dumped out, so we actually have a chimney offload state in here where you can disable chimney offload on a global basis. When you dump out, if you use netstat to dump connections, you can see for each connection whether or not it's offloaded by just using the netstat option. And then the other thing is that because we took this sort of stacked approach, we can plug in other layers. So for instance, if you have a TCP connection that's secured using IPsec, we are in the process of actually speccing out support for offloading IPsec state to a piece of hardware as well. So you can start taking the IPsec processing for a connection and offload that completely so that you're still only dealing with request level operations, send, receives, and so forth. The final piece is that the area where we continuously innovate is we're always monitoring what connections are doing and picking good candidates for moving off the operating system. The results that we get from this are actually pretty dramatic. Now, the number that I had here is actually already outdated. We were seeing 50% reductions in CPU utilization just with gigabit. At WinHEC, we demonstrated with one of our partners actually filling a 10 gigabit Ethernet connection to capacity, essentially. We're doing about 9.3 gigabits at 32% CPU utilization. And that was just with their current generation of hardware. So the way that things are starting to develop is that we have vendors who are building offload capabilities into essentially every single motherboard for like a $5 on price delta. So this is something that we anticipate having everywhere. Not only having everywhere, but also having features like IPsec support everywhere so that we can start just assuming that you can use socket options or whatever to secure connectivity using protocols like IPsec. So that's enough for bandwidth scalability. Another dimension of scaling up the networking stack's behavior is looking at what happens when you have really long paths. So you're talking from here to Zurich, or from Australia to Tokyo, or you have paths that go around the world, for instance. This has been pretty challenging for TCP, and one of the big reasons is just the sheer amount of data that you're dealing with. So if you have a gigabit at 500 milliseconds, which is admittedly a pretty long path, but just to make the point, The buffer sizes at both ends would be about 64 megabytes, and you'd have 32,000 packets in flight. Going down to 100 gigabit at the same latency, now you're up to about 3 million packets. And what happens as you have so many packets in flight is that whatever your loss rate, however low your loss rate happens to be, the probability that you'll lose a packet becomes higher and higher. And the moment you lose a packet at this kind of scale, ramping back up into the window that you had before takes longer and longer. What does that mean? So that's where we come into congestion control. So congestion control is how the TCP sender tries to avoid flooding the network. The basic idea behind it is that we try to ramp slowly into the capacity of the network, and when we get a loss, we figure that we've probably oversubscribed the network and we should back off. So that's the basic idea behind classic TCP congestion control. The problem with that is that you have to actually lose a packet in order to sense the capacity of the network. And there are alternative schemes. There are schemes that are based on sensing delay, for instance, where you keep introducing packets to the network, but then you also try and measure whether the delay in the network is increasing or not. Because if the delay is increasing, it's a sign that the network might be starting to buffer packets, and maybe you should scale back the rate at which you're introducing those packets. So delay-based schemes have been around for a while, and they have the benefit that they ramp up pretty quickly, but the downside is that when you run them side by side with the classic TCP, they just go in and suck up all the available bandwidth, and the classic TCP congestion algorithm suffers. And clearly this isn't something you can deploy on a broad scale, without addressing that issue. The way that we addressed it in Windows Vista is with an algorithm called compound TCP that came out of MSR Asia, and that's being validated by a number of research centers, including the Stanford Linear Accelerator folks. So the basic idea behind this is you start out with a loss window, which is what you would have with classic TCP, basically a window based on whether you've sensed any losses or not. But then you add on that a window based on whether you've sensed delay inside of the network. So if you've not sensed any delay, that's a sign that you can introduce a little bit more to the network. What that allows you to do is it allows you to take the ramp up that you would have with a loss-based scheme and augment that with the ramp up that you would have with a delay-based scheme without penalizing any classic TCP flows that are sharing the network path with you. So results on that. So the basic idea again is you want to avoid losses and recover quickly when someone else causes a loss, but you also want to be fair to connections using loss-based congestion control. And again, that's something that actually pays off way more than you'd have any right to expect. So we see in the scenario that I described earlier where our Microsoft.com folks were testing between Tukwila and the Bay Area, I mentioned that they got a 40x improvement right out of the gate. When they turned on the compound TCP algorithm, they got another 2x improvement. So they got another 50% reduction in the transfer time because they were spending less time waiting to figure out what the capacity of the network was. So that's basically a cross-section of some of the things that we've done in the Windows networking stack. Often I'll actually show a slide with a full scale of the features that we've implemented and the security features as well, things like secure sockets, the IPsec capabilities, the advanced firewall, and on down the list. And the problem is that there's never enough time to talk about everything that's changed. So what this is intended to do is to give you an idea for the scale of the change that we've made and how long we've spent validating the change, how much work has gone into building a platform that can evolve and that can continue to become more and more secure over time, even after we've released it. And what we ask from you is basically help in building on this foundation and taking it forward. That's a combination of things. First of all, ensuring that the tools and products you have really do light up. If there are things that we've done in the networking stack that, for instance, would impede the tools that you have out there, let us know. If there are additional features that you think would be cool to incorporate, let us know about those as well. The second part of that is to actually innovate on top of some of the capabilities that we've built. In particular, the Windows filtering platform allows you to do some very cool things. I didn't talk so much about features like secure sockets that actually allow you to use socket options to negotiate security between two machines using IPsec. Further on down the line, we introduced support for kernel mode IP helper API. So if you write drivers in kernel mode, whatever stuff that you could do in user mode using the IP helper API in terms of enumerating addresses and so forth, you can do that a lot more simply in kernel mode now. We have support for kernel mode sockets as well. So if you're writing the applications in kernel mode that use the network, we have a sockets-like API that you can use to do that much more easily. So there's no shortage of new things, no shortage of innovations that we've done, all within the scope of the kind of thinking that John talked about in the earlier talk on SWI. If you have feedback for us, here are some places you can send it. We also have content that's already out there and that's building, that's we're adding to on an ongoing basis that you can take a look at to find out more. I will be in the booth afterwards answering questions. I'll also take questions right now. We have a talk on the Wi-Fi stack, which is also completely new in Windows Vista, and which builds on a lot of the capabilities I've talked about here. And then Adrian will be talking about the heap and what we've done there. And then finally, going all the way up, almost all the way up the stack to Internet Explorer 7, the things that Dave's done and how that takes the work that we've done in the networking stack and in this Secure Windows initiative even further. So with that, questions? Yeah. Yeah. So I think the question is, if firewall vendors assume particular port ranges, how does that play with the fact that we allow the dynamic port range to move around? So the answer there is two things. First of all, if you're a firewall vendor, then you can actually lock down these capabilities. Moving the dynamic port range is a capability that you can block essentially using group policy in a particular enterprise. Now, were you asking really about port randomization, maybe? I see. So the way that the firewall platform, the filtering platform addresses that is that you actually associate the policy with the application itself. Well, if you have a specific application in mind or a specific user in mind, you can author policy that refers either to the ports or to the operations that you want to allow or to the application process itself, for instance, defined by the executable name, or to the user. So what we've done is we've tried to give you a range of options for how you take that policy and actually specify how it should be applied. Does that answer your question? If it doesn't, then I can try and understand the point you're making in more detail at the booth. Yeah. Come again? Those policies? So the Windows filtering platform actually has a filtering database where to which you can deploy filters from a central location. So for instance, I don't know if you've seen the advanced firewall user interface in Windows Vista, but that's something that either an end user or an administrator for a network can actually use to author policies and roll them out to various organizational units, various desktops, and have them take effect there. Well, once you've authored the policy, the filtering platform picks it up. So the application doesn't need to be involved. Mm-hmm. Come again? Oh yeah, an application itself can be authored to provide its own policy as well, in addition to the administrative policy. And the filtering engine is responsible for doing the arbitration around if there's a conflict, who wins. So and we have a set of rules for doing that arbitration. Yeah. And the way that we've handled that, we've done it at multiple levels. So for instance, if the firewall is accustomed to dealing with port numbers, now we allow you to actually deal with operations. So if you care about listens, about accepts, about connects, regardless of the port that's being assigned to them, we can allow you to actually say, for instance, the following application cannot connect. Or the following app. So in other words, rather than dealing at the low levels, kind of like after the fact details, after the port has been assigned or whatever, you just plug into the state machine that we provide. When we're about to assign a port, we will call out to you and say, we're about to assign the following port. You don't even have to know what the dynamic range is, because if you're plugged in, whatever the port is that we're about to assign will tell you.
Okay, so in essence, it becomes irrelevant.
Exactly, that's what I'm getting at.
Once the data is forwarded and it touches the stack, it's irrelevant.
Yeah, well, you're plugged in, basically. I mean, you can think, I mean, and that's one of the key things that I try to get across, that we're giving you a lot of control over what the stack is doing with the Windows filtering platform, and it will require rethinking the ways that you approach some of these kinds of challenges, because, I mean, it's wide open. I mean, I've heard ideas from, some of our partners on things that they want to do with the Windows filtering platform that we never even would have thought of, right? And there's more of that you can do, with what we've made available. So it's really, we have a Windows filtering platform beta program. We have the Windows Vista CDs out there. If you have the access to the DDK, you can slap on a debugger and do exactly what I just did and dump out what the extension points are. Look at the SDK, and just start to think about these things. What would you do if you actually had control over the networking stack, and you could do maybe not anything you wanted, but if you could extend it in the ways that make sense for securing desktops or solving customer problems. Yeah. Oh, I see. So that's a policy decision, and the answer is, I'll give you a couple of answers. First of all, that's something that we looked at in Windows Vista with the view to solving the problem a slightly different way. I'll tell you what the design was, but we didn't have time to implement it. The basic issue with both the connection rate limiting and with raw sockets is that we don't want to build a platform that's really easy for someone to take and turn into an attack vector. As much as possible, we want to be sure that there's an actual human being at the desktop asking to use this feature. The way that we achieve that, or the way that we plan to achieve that, is to actually tie the use of features like raw sockets and connection rate limiting into the secure attention sequence. So if you know about how user account control works, when an application tries to do something that requires elevated privileges, we switch to the secure desktop, and the user has to say allow or deny. That's the way that we wanted to solve the problem. So for instance, when someone is trying to use raw sockets, a human being has to say allow or deny, and then you can go ahead and do it. And what that does is it makes life a lot harder for a worm, right? And it also preserves the capabilities. However, we didn't have time to implement that. However, we haven't shipped yet. I can't make any promises, but my only answer is that that feature is not there today. Other questions? Thanks.